In this lecture, we are going to study the statistical decisions and the standard errors. One of the objectives of the sampling theory is to come up with certain rules that enable us to make decision about the population based on the information available with respect to the sample. Such decisions are called statistical decisions. So for reaching statistical decisions, we are going to start off with certain assumptions or guesses. So these assumptions or guesses may be true or may not be true, and these are called statistical hypotheses. In many situations, we are going to form these statistical hypotheses to see whether it can be rejected or it can be nullified, and hence it is called a null hypothesis. And an hypothesis which is differing from this null hypothesis is called a alternate hypothesis. Procedures which enable us to decide whether to accept or reject the null hypothesis or determine whether the observed samples differ significantly from the expected results in regard to the corresponding population are called test of hypothesis or test of significance or rules of decision. Next, we will look at the standard errors. There are mainly two types of standard errors. One is type 1 error. By an error of judgment, suppose we reject a hypothesis, but it should have been accepted. Then we say that type 1 error has happened. And then comes the type 2 error. By an error of judgment, suppose we accept a hypothesis, but it should have been rejected. Then we say that type 2 error has happened. Next, we will consider problems based on type 1 and type 2 errors. Here is the first problem. To test the hypothesis that a coin is fair, the following rule of decision is adopted. Accept the hypothesis if the number of heads in a sample of 100 tosses is between 40 and 60, or else reject the hypothesis. They are asking you to find the probability of occurrence of type 1 error. So let us say that x is the number of heads occurring when we toss a coin, and n be the number of tosses. Here in this case it is 100. So if the coin is fair, then the probability of getting a head is 1 over 2. So your x will be binomially distributed. So the mean of the binomial distribution is given as mu is equals to n into p, which gives us that to be equals to 50. And sigma is given by square root of npq, or this is square root of 25, which gives us 5. So the corresponding standard normal variate is given by the formula z is equals to x minus mu divided by sigma. Here in this case it is equals to x minus 50 over 5. Here we are going to find the probability of x lying between 40 and 60. That is, the number of heads is lying between 40 and 60. Then we consider the coin to be fair. So substituting x in this z, we will get the z value lying between minus 2 and 2. And this is equivalence to f of 2 minus f of minus 2. Looking up at the normal distribution table or using your calculator, we will be able to find that f of 2 is 0.9773 and f of minus 2 is 0.0227. So that gives us 0.9546. So the probability of not getting heads out of 100 tosses between 40 and 60. So this is the probability of getting the number of heads between 40 and 60. But we need not getting between 40 and 60. So the probability of x not lying between 40 and 60. So that will be equals to 1 minus 0.9546, and that is given by 0.0454. So that is, we can say that the occurrence of type 1 error is 0.0454. Okay. Let us move on to the next problem. Here is the next problem. For the purpose of estimating the mean of an infinite population with standard deviation 2.4, the following rule is adopted. The population mean is estimated as 20 if and only if the mean in a sample of size 36 is less than 20.75. Find 1. The probability of occurrence of type 1 error. 2. The probability of occurrence of type 2 error when the population mean is taken as 21. So first let us write down what are given to us. Standard deviation is given, which is sigma equals to 2.4. Then the sample size is given, which is 36. And they say that the mean population mean is equals to 20 if and only if the sample mean is less than 20.75. So first let us look at the first case. They are asking you the probability of occurrence of type 1 error. So if x bar is less than 20.75 and mu is equals to 20, then there is no error, right? And if x bar is less than 20.75 and mu not equals to 20, then we say that there is a type 1 error, right? So with x bar is equals to 20.75, mu is equals to 20, and sigma x bar would be equals to sigma divided by root n, which is 2.4 over square root of 36, which gives us 0.4. We can find what is z. It is equals to x bar minus mu divided by sigma x bar, which is 20.75 minus 20 over 0.4, which gives us 1.875. So now let us find the probability of x bar less than 20.75. It is equivalent to probability of z less than 1.875, which is equals to f of 1.875, which is found to be equals to 0.9696. So here there is no error. If x bar is less than 20.75 and mu is equals to 20, there is no error at all. Then the probability of type 1 error would be 1 minus 0.9696, which is equals to 0.0304. So this is the probability of type 1 error. Let us move on to the next case. We need to find the probability of type 2 error when the population mean is taken as 21. So your x bar is still less than 20.75, but here we are going to take mu to be equals to 21, and we have already seen that mu is equals to 21 sigma x bar is equals to sigma divided by root n, which is 0.4. So your z would be equals to 20.75 minus 21 over 0.4, which gives us minus 0.625. So the probability of x bar less than 20.75 when mu is equals to 21, it is equivalent probability of z less than minus 0.625, which is f of minus 0.625, which is found to be equals to 0.266. So that is the probability of occurrence of type 2 error is 0.266.